ecology of ideas. And it's very important that we work simultaneously on different approaches to solving the same problem, because we learn a hell of a lot more by having arguments about the nature of quantum gravity at conferences from, say, somebody from another camp, because they ask questions in a different way, they think about things in a different way. It's important that we maintain a healthy ecology of different theories all trying to describe the same thing. I mean, you could argue also that causal sets is an approach towards quantum gravity. You know, there's a number of buzz phrases that you can talk about, which aren't string theory, that do attempt to describe quantum gravity. It's just that none of them has, for example, you know, calculated from first principles the entropy of a particular kind of black hole, which string theory has managed to do since 1996. Others, for example, loop quantum gravity, people will tell you with a straight face that they've done that too, but in fact they haven't. There's a big hole in the argument. There's certain constants that they can't fix, and they wave their hands about it. But, you know, so again, there's what is talked about in the popular media, and there is what happens actually on the ground in real life. And I don't want you to think that actually loop quantum gravity, as presented by people like Lee Smolin, is a serious competitor to string theory. At the moment it isn't. It hasn't loop quantum gravity has nothing to say about any standard model physics. It doesn't explain the mass hierarchies of different particles in the standard model. It doesn't explain the strong CP problem. It doesn't explain the hierarchy problem of the Higgs mass. It doesn't explain a hell of a lot of stuff. And so, you know, that's why I don't feel compelled to work on it at the moment. But I feel compelled to, say, spend 1% of my time learning about a 1% or 0.1% minority opinion about how gravity works, and it's very useful. I just don't think it's right. So, you know, but time will tell. We will find out, and just don't believe everything that loop quantum gravity people tell you. But don't believe everything the string theorists tell you either. But at least, yeah, I hope that goes some way towards answering the question.
I want to know how many these atom smashers are around the world, and which one is the biggest. And I also want to know, because you mentioned that when you smash those atoms, you have a tremendous amount of energy. If this is considered to be renewable energy and it could be utilized in the future?
Right, so there's two separate questions. One of them is about what are the biggest, meanest atom smashers in the world, and that's actually a fabulous question. I should have answered that earlier. Before this LHC machine, this Large Hadron Collider, which is, by the way, it's not a Large Hadron Collider, which is a very easy misspelling. But this Large Hadron Collider, the LHC machine, God, I don't know where the hell that came from. I've had a really long day today. 1 hour of lectures, 2 hours of presentations, prospective graduate students, interviews with prospective graduate students for hours and hours, and then come in here and give a talk about string theory. So the short answer is there are other smaller accelerators in other places, but they're nowhere near as impressive as this thing. This machine is 7 times more powerful than the most powerful of its predecessors. So up until now, the energy frontier was at the Tivatron at Fermilab, which is out in a paddock, you know, out in the boondocks near Chicago. So there's this big ring, but it only manages to accelerate the little things that get smashed together to about 1/7 of the energy that will be able to smash these protons together inside the Large Hadron Collider. So there are quite a few particle accelerators around the world. There's one in, for example, in Cornell that's been studying physics of bottom quarks and things that make it up, that's taught us a lot about how the asymmetry in the universe arose between matter and antimatter. Have you ever wondered why there's stuff and not anti-stuff everywhere? So, here's the question. If in the universe there was a bunch of anti-stuff around, and there was a bunch of stuff, well, the universe, when it was very wee, when it was when it was born, was very small. So presumably the stuff and the anti-stuff would have had ample opportunity to find each other and slam into each other and make pure energy. So they would have annihilated just into radiation. There wouldn't have been any stuff left over or any anti-stuff left over. They would have exactly cancelled. So how was it that there was an abundance of stuff over anti-stuff that arose in the universe? When did it arise? How did it arise? And asking those sorts of questions is something that we really want to know. So that's part of what the Cornell machine has helped us understand. There's also a big particle accelerator at SLAC, the Stanford Linear Accelerator Center, and that was the first particle accelerator that I ever saw. It was just down the road, 3 miles away from where I was sitting on campus as a graduate student. So there's a whole history of smaller machines that has preceded the construction of this gigantic, super enormous, several billion-dollar LHC machine. But in the whole world, the world doesn't have enough money to build even 2 LHCs. As it stands, the countries and governments of over 70 countries around the world have had to get their politicians, all of them, to agree to fund this huge, ginormous international project. And some governments have put in billions of euros and, you know, large amounts of money. Other countries, like little old New Zealand, has put in little weeny amounts of money, but we contribute what we can. So the fact that so many people have all agreed and made peace, you know, in the name of particle physics, just to get this project together, it tells you something about how excited we are to be pushing the energy frontiers. And as it stands, there's only one LHC, and we probably, as humanity in the current era, don't have enough money or political will to build another really huge particle accelerator, at least not this decade probably. So the question is, when, after what happens if we run the LHC for 10 or 15 years? Is there going to be another machine? We don't know. That's one reason why it's so crucial to the field that we get data from this machine that tell us new things about the universe, because building an even bigger atom smasher might be just so prohibitively expensive that we can't justify it as a human race. We've got a lot of problems on our hands. And understanding the fundamental structure of force and matter through all the epochs from the birth of the universe to now, from the microscopic out to the edges of the universe, that might not turn out to be a big priority. We don't know. So to answer your question, there are American machines, European machines, Japanese machines, lots and lots of particle accelerators in lots of different places. The first ones were only tabletop size, but now we're having to build rings that are, you know, over 10 kilometers around, and things that are just using so much power that it's insane, you know, to smash these things together. Now, so just to give you a sense, this is the biggest machine, and it may be the biggest one ever built. But what they're doing in order to check that we're not producing BS in this experiment is building two really big multi-purpose detectors at different points on the ring and having the smashings occur at both places, but independent from each other. Totally different detectors, different designs, different people working on them, totally different architecture. So the idea is, we've got these protons going around in these counter-rotating beams, and we make them smash into each other at this thing called Atlas. We make them smash into each other at this detector called CMS. Those are the two biggest detectors, and they're going to be checking each other's results. So it's important that we have, at the very least, two big detectors in this one gigantic atom smasher, this particle accelerator, so that we can check that if we discover something in, say, Atlas, that it isn't just a fluke or a mistake, that if CMS sees it as well, then we can be sure that we've got something, and then we can go and announce to the universe, hey, we discovered the Higgs, or whatever. Now, the second question that you asked is, you know, we're throwing these protons at each other in the LHC machine with such stupendous energies. You know, we're trying to recreate conditions partway back towards the Big Bang. I mean, this is how extreme the physics is going to be. The physics inside this particle accelerator is going to be the most extreme physics anywhere in the vicinity of our planet, save for maybe the black hole at the heart of the galaxy, you know, munching a whole lot of stuff at its very center, or the singularity that created the Big Bang in the first place. So this is going to be like extreme physics, you know, like extreme skiing or something. This is really extreme stuff. The unfortunate thing is this energy, it's all sort of wasted. You know, we try to be as conservation-minded as we can, but the amount of energy it takes to run this accelerator is enormous. You know, you wouldn't want, for example, here's an example of just how much energy it takes to run a particle accelerator. The SLAC machine, which is smaller than the LHC by many times, you know, 1,000 times smaller or something, just rough order of magnitude. When I was a grad student at Stanford, which was only 1990 to 94, you couldn't run the Moffett Field wind tunnel at the same time as SLAC because they put too much of a drain on the Bay Area power grid. So these are big-ass machines, and they use big-ass amounts of power. So the LHC is going to have, you know, $1 million plus power bill per year. I mean, it uses a hell of a lot of energy. So, but unfortunately, you can't sort of regenerate it. Something called the second law of thermodynamics, that you can't have something for nothing. And unfortunately, you can't use this power in a way that would help you solve any energy problems of humanity. We're much better off, if you're worried about energy policy, ignoring particle physics and going and building better solar arrays, using more conservation, driving hybrids, driving electric, whatever's, using our human horsepower to get around. So I'm sorry to give you a depressing answer to your second question, but it's just depressing, and you burn all this energy and it's wasted and you can't get it back. But, you know, you try to recover as much as possible. So, for example, at SLAC, the place where they dumped the beam after it had been used up as much as it could, they used the waste power to heat the dorms. So, you do what you can. Please.
Hi.
Please stuff your face right in the microphone, otherwise I won't hear you, and neither will the guys in the back.
When it comes to strings, is there only one type of string that vibrates in different ways? Okay, and are the different sort of particles and photons have different masses? Is this due to different string lengths, or?
It's due to different kinds of vibrations of that same string. So you've hit on the central idea of why string theory is a unifier, why you can even use it to talk about these two very different regimes and under the same umbrella, is that very central idea that you mentioned, that there's just one kind of string. You can cut it so that it's got ends, or you can join together the cut strings so that they join up again. It doesn't have ends, but it's all the same basic kind of string. And the different particles arise, as you said, like the photon or the electron or quarks or whatever, from that same single kind of string choosing to vibrate in different ways. And you're right, strings could also have different lengths. There could be a string that's really fat and chooses to dawdle around for a long time before it comes back on itself, or there might be a tight little string or whatever. But we do know at the very least that whatever these strings are doing, they have to be small enough to fit inside the subatomic particles that we think we see already today.
Okay, that's the second thing I wanted to ask about was these subatomic particles, quarks. It sounds like there's more than one string in these, or are they one string?
Okay, so the notion is that there would be one little vibrating string which would be vibrating in a quark way. Instead of vibrating like an electron, it would be vibrating like a quark or something. And maybe it vibrates like a photon in a different fashion. But the notion is that for every subatomic particle that's supposed to be represented by some string thing, there would be one string per particle. And the different particles are represented by different musical notes, different vibrations of that same fundamental string.
And each of the forces, the photons that make, those are strings as well.
That's exactly right. So the messenger particles, I should have had you give the lecture. So the little messenger particles, or if you'd asked your question earlier, if you'd given yourself the credit of realizing it was a great question, those little messenger particles that are supposed to represent the forces between the subatomic particles, those are also little subatomic particles themselves, as we learned with our little medicine ball and ice skaters analogy. And you're right, the photon is represented by an open string vibration. And the gravity particle that transmits the gravitational force, that might have been gravity that caused that. But that little graviton that represents the exchanges of graviton that represents gravitational attraction, like between you and me or whatever, or like the moon and the earth, those are represented by little closed strings vibrating. Thank you. Thank you. That was a really fabulous set of questions. Please go ahead.
Thanks for a great talk. I apologize in advance if this is a naive question because it's coming from a biologist.
There's no such thing as a dumb question in a physics lecture.
Okay. I recently noticed that string theory cropped up in the context of the evolution versus intelligent design debate.
String theory is in the ID versus... Wow, that's pretty interesting. I didn't realize we had anything to contribute to that.
It is quite bizarre, I have to say, but it came up in the context of, in the sense that often when intelligent design theorists want to have their theory taught in schools, they're told that it does not qualify as a theory in the scientific sense because it doesn't make any hypotheses which are testable and falsifiable.
Like string theory, yeah.
And some people have suggested that in fact string theory is similar in that it also does not put forward any unique hypotheses which are falsifiable. So
that's actually wrong, but...
So my question is, have you heard that and do you think it holds any water?
Yes and no. But the longer answer to the question is, so why would string theorists even be, in the firing line, so to speak, in this ID debate and so forth? And I think the point that you made, you said, well, it seems like string theory at the present hasn't been discovered experimentally. I haven't come up here and shown you a string, because it's just at the moment an idea that has a lot of things to recommend it, but so far we haven't actually seen evidence of a string in an experiment. So it's just a hypothesis. However, and here's the big however, which is that in order for us to construct this beautiful thing called string theory, which has in it all of particle physics, all of general relativity, and then some, So it's a complicated animal. In order for us to be able to construct, well, sorry, I'm just trying to think how to say it in the best way. We have to insist that at every stage when we build this sort of super duper string theory of our story, that in limits that we're already familiar with, like if we took off our glasses and we went very far away so that the string did look like a point-like particle, or if we take limits of the string theory that we're familiar with already, give back classical physics that we know and love, or it gives back a theory of particle physics that we've already studied, string theory has to be consistent with the results that have already been obtained. And that's what makes string theory different, completely different, than intelligent design. Intelligent design doesn't have any logical structure to it whatsoever. String theory has a huge amount of logical structure to it. It's consistent with all known physics of the 20th century, including all of the experiments that were done to test 20th century physics. So every single one of the experiments that has tested, say, the theory of quantum electrodynamics, that's just when you put quantum together with electricity and magnetism. Physicists invent these really scary sounding names, but they're not really that impressive after all. So quantum electrodynamics has made predictions, for example, for certain physics things that are correct to 12 digits of decimal places in a measurement. So string theory also can claim that as a success because it has in its limits things that we already know and love or familiar with. But intelligent design, again, doesn't have any sense of correspondence principle. There's no sense of limits of when you give something a greater degree of approximateness and you look at it with a more coarse-grained analysis, you look at it with a broader brush, you don't get back what you're already familiar with. There's no sense in intelligent design that it wants to be consistent with prior ideas. But string theory rests on the bedrock of those twin pillars of 20th century physics. It contains as one of its pillars, the whole construction of quantum physics, and every part of quantum physics that's relevant goes into making things like my little iPhone work. I mean, if nobody had given a damn about the structure of the electron and tried to understand its properties in the 1930s, we wouldn't have any of these devices or laptops or fluorescent lights or a whole bunch of other stuff. Now, I'm not trying to say that physics is the be-all and end-all of everything. It isn't. But just when people say string theory is not testable or that it doesn't make unique testable predictions, that's a perversion of the meaning of those phrases. And it's not technically correct. So it's sort of, you need to be a bit careful when you hear people criticizing the hell out of string theory. A lot of it comes from a place of sour grapes. Perhaps 2 recent popular books might have been examples of something like that. That's as much as I'm going to say about either of those 2 authors. Even if you ask me, I'm not going to comment because it's being recorded. I'll be much ruder in private, but I'm trying to be on my best behavior in front of a group of impressionable people, and so I'm trying to be an example of what I'm trying to advertise that we're about. So I'm not going to stand here and get all negative about things, but just be a bit careful when you hear people say string theory is not testable. Well, it's just not true. And there are ideas in particle physics that we don't have a hope of directly testing in the lab anytime soon either, but we can learn very important things about things that are supposedly to do with smaller distance scales than we can measure or higher energy scales than we can measure, but by being very clever, we can learn things indirectly. So we may never be able to build a stringotron that that'll bash protons together strongly enough to be able to create strings in the lab. We may never be able to build a Planckatron where we can make quantum gravity appear at will in the laboratory, but that doesn't mean we can't learn about it. For example, there are now thought to be black holes at the center of over 90% of the galaxies in the universe, and these are caused by things just creating and bashing together and gravity pulling them together. For example, at the center of the Milky Way galaxy, there's about 1 million solar mass, or billion solar masses. These are really, really big black holes. And so if I stand here and say that there's a black hole at the center of this galaxy with a mass of that much, how do I know? I haven't gone and measured it. You might accuse astronomers of lying through their teeth and making untestable predictions. You can't go over and measure that black hole. What the hell are you talking about? How do you know that there's a black hole there with 95% confidence level at the center of the galaxy and it has a mass and such? Well, we do it indirectly. We don't reach out and touch the black hole. We can't go there in a finite amount of time, and we're certainly not going to chuck our graduate students down the black hole to check, because they can't go back and tell us about what it was like afterwards. So you can do a lot with science without being able to directly, you know, make what you're trying to study directly right there in the lab for you to see it with your personal apparatus. So the story of science is partly that it's about ideas that can be applied in all different circumstances. That the laws of physics are it's the same electron that's emitting a line in the hydrogen spectrum, whether it's in Alpha Centauri, whether it's in my body, whether it's in my laptop, whether it's Mars, Montreal, Andromeda, or the other side of the universe. They're still the same electrons. We don't know that for certain, but we have every reason to believe in all the ones that we've looked, they're all the same. You know, so we make an assumption. We believe that the same electrons are in the hydrogen atoms that are on the other side of the universe, which is how we know about the evolution of the universe. Again, we haven't gone and checked. Not testable. You know, so the word testable, you can pervert it and use it how you like in a popular discussion. But when you're a scientist, you have to say to yourself, what does it mean to test a theoretical idea? And the very first part of testing a theoretical idea is being precise about what the hell you're talking about. So making a definition, making a logical deduction series of things that make sense. And, you know, physics, string theory is a part of modern physics, which is rooted in particle physics. And string theorists, we still consider ourselves today, and we still will for as long as I can think of, consider ourselves a subclass of particle theorists. So people study physics of high energies, and if you're a theoretician, you do it with particles or with strings. But we're just a group of physicists among many kinds of physicists. Some of the other physicists in my department study the physics of rocks and, you know, atmospheres and other planets and goodness knows what. But, you know, science has to make a set of assumptions about the way the universe works in order to be able to get anywhere. Like, I do have to assume that it's the same hydrogen in Andromeda or on Mars or in Montreal. I have to make that assumption to be able to do science. So there are certain assumptions that, yes, I can't prove, that can't be tested. Nonetheless, there's a very serious set of steps that goes into formulating scientific principles, which says at the very least you've got to check consistently with everything that's gone up until now. And then if you're going to propose some new ideas, you know, whatever. So, you know, the process of building string theories of the universe is not nearly as arbitrary or as stupid as you might believe by reading critical discussions of it in the popular media. In fairness, though, the successes of string theory are probably not as wild as Brian Greig would have you out to believe by watching The Elegant Universe or reading his books. So he's overly optimistic, I think, about a number of things that workers in the field would be a bit less evangelical about. But maybe that's partly because he's just good at expressing himself. I mean, the guy can certainly write. He can write me off the face of the earth. I mean, so, you know, people who have the ability to communicate about their science with the public, I think, have a real responsibility to do so as part of that public trust that we receive your tax dollars. We apply for it very competitively, but we still get taxpayers' money in the form of research grants from the government. And part of our responsibility is to try to give back an appreciation of what we do to the general community. So I don't know if that goes some way towards answering your question, but I appreciate the intervention. Please, go ahead, sir.
And I think this will be your last question, unfortunately.
Okay. With the answering of the former lady's question on how like if this particle accelerator that's being built will be able to elucidate ways in which we could go about generating more energy, right? A new form of, a new powerful form of
During the smashing,
generation. I feel like this is almost like a pretentious furthering of physics reductionism, which is like what are the concrete benefits that this is most likely to yield, right? Like,
right.
I haven't understand it. Like, it feels like physicists playing around with these little particles that is like who cares? Like,
that's an exception.
How is this going to benefit me? Sure, it may assert string theory in more ways, but like, what are the
Who cares? Or why would it be relevant to the life of an average human being
like,
in the year 2008?
Like it's like the space program. Like we're off there exploring, sending space shuttles up and down, but we can't even get our world right. Like, you know,
right.
It's ridiculous.
This is a good point. So I think there were more than one question in your question, but one shouldn't build a particle accelerator like the LHC because one believes that one will get a new form of energy out of it. Anybody who tries to justify building a particle accelerator on the basis of maybe producing, if we're lucky, a new form of energy that would solve all of humanity's problems, they're lying through their teeth.
Yeah.
So, you know, some people justify the millions and billions of dollars we try to spend on producing nuclear fusion in the lab because we know that it powers the sun and it powers a lot of other really interesting things in the world. I mean, you know, nuclear fusion and fission are what make suns shine in our galaxy and other galaxies. I mean, we'd have any light to collect if they weren't going running on nuclear power, all the suns in the universe, which